Hello everybody and welcome to this last video on logs and exponential. Today on the agenda of part 3, one topic, logarithmic differentiation. And then that's it. After that we're moving into the applications of derivatives. So much more practical, much less theoretical. It should be more interesting. But I thought that before going into this last part of logs and exponential, I think it would have been nice to actually just make a quick resume. So let me just put this over here. Let's call that summary of all the rules of derivatives, all of them, everything we've seen so far. So of derivatives, some sort of a complete list if you want. So the complete list. So in our notes, one page, and all the rules for derivatives all located in one place. So let's go over that. Rule number 1, the derivative of a constant. Oh, this is going to take us way back. Now these are like easy rules by now because we have become much better at this than we were a month and a half ago. 3, the derivative of x, then the derivative of a constant times x, then the derivative of x to a power of n, and the derivative of a constant times f of x, like this. These were the first 5 rules you probably remember. 0, 1, c. This will be, of course, n, x to the n minus 1, and this is the one that allows us to take out the constant and just basically put the prime, put the derivative to the f of x itself. Then we have rule 6. Move it a bit to the left here so I have enough space. Rule 6, this is f of x plus or minus g of x, the derivative of that. And then rule 7 was the product rule. We've used that abundantly. Then rule 8. Remember rule 8? That was the quotient rule. Yes. F over G. Rule number 9. We actually went into something that we actually called f of x to the power of n, the derivative of that, the so-called power rule for function. And basically then we went into the trigs. So this was the derivative of sine of u. Then what are those? This is, of course, f prime plus or minus g prime. Yeah. This is the product rule, so f prime g plus f g prime. This is f prime g minus f of g prime. You will remember that this is over g squared. Yes, g of x all squared. We know this, we've got that. This is n f of x to the n minus 1 times f prime of x. This is our first encounter with chain rule. And this is cos u times u prime, another encounter with chain rule with a u prime. And then we get into like the later ones, so 11, 12, 13, 14, 15, 13. We had here the derivative of cos u. Let's fill this in right away. What's the derivative of cos u? Minus the sine of u times u prime, of course. And then we went into the very latest developments that we looked at in the previous video, namely the derivative of the exponential e to the u. And then we had ln of u. So let's fill in those two. What's the derivative of e to the u? You may remember it to be e to the u times u prime. And the derivative of ln u would be 1 over u times u prime. And the last two are variations on 12 and 13. Instead of having e in here and log base e in here, we have a to the u, where a is any positive number. And we have here log to the base a of u, where again, for these two, it is understood that a is a positive. A is a positive. What happened to my red? A is a positive. Oh, that's dead. So a is a positive number. So a is a positive number. And the last two, as you know, well, that's a to the u times u prime, chain rule, and this has this extra particle called ln of a. This one, well, just looks like 13, so 1 over u times u prime. And because it's log base a and not log base e, we have to go 1 over the ln of a. So, like I said, it's kind of nice to have all the rules in one spot, and we can refer to that whenever we need to find any derivatives. And that's a complete list. We will not add on to this between now and the end of the course. So let's get rid of this and let's go to our actual topic of the day, which is logarithmic differentiation. What is this? What a complicated name for a technique that will probably remind you a little bit of implicit differentiation, another technique to derive that we have seen earlier. So, log diff, logarithmic. By now you know that the word differentiation refers to the derivative, right? So by logarithmic differentiation, we simply mean derivative using some log technique. So when do we use this? When do we use this? To be used whenever we have a function h of x that actually is written like a function f of x to a power of another function g of x. So notice here that there shall be some x's in the base. There will also be x's in the exponent, right? So example, if y equals, I don't know, root x to the power of sine x, see here, x in the base and x in the exponent. If we have that, then we need to use, then to find y prime, we need to use, to find y prime, we need to use log diff, logarithmic differentiation. Pourquoi? Well, precisely because x in the base as well as x in the exponent. You see, we've covered all cases so far. So recall, before I get into the details of the algorithm to actually solve this, recall if you have a constant to a power of a constant, right? I don't need like brackets here, I need like smaller brackets. If you have a constant to a power of a constant, the prime of this is easy to get. If you have a constant to the power of x, the derivative of that we know as well. If we have an x to a power of 2, I think we know how to do that as well. But if we have an x to the power of x, now that is not something that we know. What is the derivative of 2 to the 2? What's the derivative of 4? It is 0. What's the derivative of 2 to the x? Well, isn't that rule 14? 2 to the x, x prime ln 2. What's the derivative of x to the 2? Valo, that's easy. 2x. And that, we don't know. Because that's x to the, in the base and x to the power. That is actually a case of logarithmic differentiation. So when you actually make the base and the exponent vary from constant to variable, we've covered the first 4 cases already. This is the last case we have to look at. So let's do just that. Okay, so I'm going to get rid of this and start a new whiteboard. And I will explain the technique involved, which is, like I said, similar, well, at least in certain regards, to implicit differentiation. So to perform log diff, to perform log differentiation, follow these 6 steps. What are the steps? Step 1. Step 1. Call the function, call this function y. Whatever they give you to derive, like x to the x, or root x to the sine x, whatever, don't call it h of x, don't call it f of x or anything. It must be called y. Okay, you're going to see an example how this pans out. So step 2, take the ln, take ln, take the ln on both sides. Take the ln on both sides. Step 3, use the property of log. Remember there are 3 property of logs, and if you really paid attention to that little segment of a previous video, I put a little star next to the 3rd one because I told you that's the one that's going to be important. Well, that's exactly what's going on here. Use the property that ln of x to the y, I shouldn't use y because I have y already. Let me use another name. Ln of x to the a is actually equal to a ln of x. Okay, so step 4, prime both sides. So derive both sides. Okay, once you have that, you will have a y prime. So step 4, isolate y prime. Why will you have a y prime? Because of step 1, because you called the function originally, you called it y. And finally, step 6, don't forget to replace y by the original step 1. By the original step 1. So we'll keep that in mind, and we'll apply this technique, the 6-step technique, to a simple function for which logarithmic differentiation applies. So let's get rid of this. We can actually work this all out on a problem. So let us start with something relatively simple, although even in this section the simplest problem is 3 stars. So example 1. Example 1, 3 stars. Evaluate the derivative of x to the x. Okay, so x in the base, x in the exponent, that means we will have to use log diff, logarithmic differentiation. So not log, x in the base, x in the base plus x in the exponent. This implies log diff, logarithmic differentiation. So x in the base and x in the exponent, log diff, like we have here. So step 1. What is step 1 if we look back? Call it y. Call the function you want to derive y. So y equals x to the x. This is the function you want to derive. Step 2. What is step 2? ln on both sides. So ln of y is equal to ln of x to the x. Step 3. Use the property of log that allows you to take the exponent in front of a log when it is expressed in this way. So ln of y is, what happens here? This exponent comes right in front of the ln. Comme ça, x, ln x. Step 4, this is where most of the work will take place because this is where we actually derive both sides. Step 4, ln y prime x, ln x prime. All right. By now, you're most likely acquainted with the fact that this is going to be a product rule. You can see the times right here that I've highlighted. So how do I derive this? ln of y. Well, isn't that rule 13, right? ln of u. What's the derivative of ln of u? 1 over u, so 1 over y, times u prime, so times y prime. 1 over y, y prime. Now this product rule, yes? So x prime ln x plus x ln x prime. I still have a couple of primes in here, so I'm not done. I am not going to touch this because exactly like an implicit differentiation, y prime is what we want to have at the very end. So 1 over y, y prime, this remains untouched. X prime, rule 2, plus x times ln x, that is rule 13, isn't it? So this goes 1 over x times x prime. Good. Oh, one more prime in here. So 1 over y, y prime equals to 1 times ln x is ln x. And that is x times 1 over x times the derivative of x, rule 2 is 1. So what I have here, really, a little bit of simplification, very little, shows that this is ln x plus 1, right? Because x over x, these two guys will go away. The only prime left is here with the y prime, which means I am done finding my derivatives. I am done with step 4. So step 5, isolate the y prime. So what do I do to isolate the y prime here? It's got a 1 over y in front of it. So all I got to do is multiply both sides by y. So ln x plus 1. So multiply the y to the other side, and that's that. Finally, step 6. Don't forget to replace the y. See, now you know what I mean, huh? There's a y here. And in step 1, we actually called y x to the x. So now it's a time to replace this y by what we called it earlier, step 1, and that will give us our final answer. Y prime is this, x to the x, ln x plus uno. And that is the outcome of logarithmic differentiation on the function y equals x to the x. Good enough? Good enough. Let's practice this technique on another example. So what could we have? What could we have here? They're pretty much all revolving around the very same strategy. So example 2, we could have perhaps another 3 stars. So evaluate something like sine x to the power of cos x derivative. So once again, what do I notice here in this function? I notice that I have an x in the base as well as an x in the exponent. So that's a case for logarithmic differentiation. So again, you will notice that there is x in the base and there is x in the exponent. So x in the base plus x in the exponent equals logarithmic differentiation. All right. So let's apply our steps on this. Step 1, whatever function that you're supposed to derive, you need to call it another name. Y will do the job, so call it y. Sine x to the power of cos x. That is my y. Good. Step 2. What do we do in step 2? We need to remove the cos x from its exponent position to something in front, and we can do this first by taking the ln on both sides, and we do that in order to use the property that actually says, well, I can take that exponent straight in front of the ln. So now we have that ln of y is equal to cos x plus the ln of sine x. Step 4, where most of the work gets done, we shall prime both sides. We shall prime cos x times the ln of sine x. We shall prime both sides. You will notice that the prime of the left-hand side will always be the same. This is always 1 over y times y prime. That never changes. Well, as for this, here we go again. It's always going to be a product rule, because when you bring this in front, that's what you create. You create a product of two functions. So that's going to be cos x prime ln of sine x plus cos x times the ln of sine x prime. So 1 over y, y prime becomes, we know this is one of our dear rules, I do believe, rule 10. It's minus sine x times the ln of sine x. Oh, here, yeah, when you do this, it's basically minus sine x times x prime. But x prime is what? It's 1, right? Okay, plus cos x. Now, I want to point out that when I derive ln of sine x, I'm actually deriving the ln of u. And what's the derivative of ln of u? That is rule 13. So 1 over sine x times sine x prime. One more prime to go, and I can move on to the next step. So 1 over y prime is minus sine x ln sine x plus cos x times 1 over sine x, and the derivative of sine x is again cos x. Now all the primes are gone, right? All the primes are gone, so isolate the y prime in step 5. How do I isolate the y prime? I again cross multiply the y to the other side. Easy step. So just cross the y to the other side. This is just a whole long rewrite. Sine x plus. Can I do this? Would you agree with me that 1 over sine times cos can most likely be written in another fashion? Just say I want to simplify a little bit, just for the halibut. 1 over sine times cos, that's the same as what? Cos over sine. And what is cos over sine? We know that. Cos over sine. If you answered cotangent, you're right on the ball. Cosine over sine, c'est la cotangente. Finally, step 6, we want not to forget to replace the y that is here with its original name that we have given it in step 1. So y was sine x to the power of cos x. So here we go. That's it. That's all. Good night, folks. Sine x to the power of cos x times rewrite minus sine x ln of sine plus cosine times cotan. And that's that. It's not very pretty, but it is accurate and it corresponds to the answer. I hope this is clear enough. And of course, when we go to class, we'll practice some more. When we do a lab, we'll practice some more. When we do a quiz, we'll practice some more. We'll keep on practicing because practice makes perfect. In the meantime, hasta la vista.